All right, I think we're just about ready to get started again. My name is Squirrel Eiserloh. I'm a game designer, programmer, and I currently teach at SMU's grad school for game development. And I'm going to talk about randomness in games. Just really quickly, my background is in design and code. I've come up through code mostly. I've been in the game industry for a while. This is my 9th year presenting at GDC. Now I'm an indie game developer. I've gotten out of AAA. My background and degree is in physics, and I'm teaching currently. I worked at Ion Storm, Ritual, Mumbo Jumbo, True Thought, and I was a lead programmer or technical director at those companies. And worked on a bunch of different games in a bunch of different genres, 2D games, 3D games, AAA, indie, etc. So my motivation in trying to think about what I wanted to say about randomness in games came down to, I think, this sentiment, which is that the game programmer is the bottom line of the design chain. And by that, what I mean is that the designer comes to you and says something has to do more damage, or it has to go faster, or slows the person down. Well, what if you have two of those effects? Are they multiplicative? Are they additive? Oftentimes, those things aren't specified, right? Is there diminishing returns? You have 5 guys building a building. Is each one contributed a linear amount, or is there some other math that's going on there? And so oftentimes, those decisions are left to the programmer. So the programmer has to ultimately wear the design hat. Even an engine programmer has to decide how these kind of tools that are exposed, how they're exposed and how they work under the hood. So there's a lot of sort of designy bits in here. In this talk, but that's partly because I really want to emphasize the importance of the nuances of design in terms of the ramifications of the decisions you make in terms of the way you write your code. Hopefully that will be apparent. Okay, so why do we use randomness in games? Why do we care about randomness? There are a number of reasons, I think. One is variety in circumstance. Some people might call this input randomness. No one would ever play solitaire if the cards were always in the same configuration when you started, right? And it's obvious, but it provides variety of play. There's variety in outcome, also known as output randomness. This is, I hit you, this time it did 5 damage, next time it did 15 damage, or sometimes it does a critical hit. But that's really not something I have control over. Maybe I can pick a weapon that procs more or does crits twice as often or something like that. But at most, it provides a risk-reward sort of effect. Randomness can offer replayability with, for example, roguelikes, which tend to have dungeons that are completely randomly generated. You can play the same game over and over and over and never get tired of it because the challenge is always different and new. And that's true with a lot of games, right? Alpha Centauri, Civilization, Magic the Gathering. You can play the same deck of cards and have different outcomes. It's interesting, and we'll get into pseudo-randomness, that random numbers are not actually random in computers, and that's kind of annoying, but it's also a brilliant, can afford a brilliant side effects like reproducibility. For example, Minecraft Seeds.info is a website, among others, that exchange seeds for random numbers, which we'll talk about. That if you punch that in, then you're going to randomly generate the same exact world that I randomly generated. And you can go over to that mountain, and on the other side, there's that same lava fall. And that can be useful for a number of reasons, too. Randomness is also really useful for making things seem organic, right? In these example, these orcs, this is not computer graphics, but every one of those orcs is a little different, and that's what makes them feel alive. Right? When monsters in a game all look the same, when they all move the same and act the same and decide the same, they don't feel organic. So randomness can come to our aid there, too. There's also a sense of fairness that we might want to talk about, where players feel like they're getting lucky or unlucky. Sometimes that's true. Sometimes that's not true. So my goal here is to go really fast through this. I only have 35 minutes to cover this. I'm going to try to throw some tools in your toolkit, but mostly so you can go back to the slides if you want to get into the details, but I'm just trying to prime the pump in terms of ideas of what we're talking about here. So we'll get into a number of these different things. We're going to give you some simple code toolkits as well, dealing with Perlin noise and random noise and smoothing and some other stuff. Okay, so the most basic form of randomness in programming, say I'm going to be thinking in C and C++ for this talk, returns a random integer. And rand has been around since forever. And typically the way it was used was we would call srand to seed a random number, because heaven forbid we write out what it actually is. And that determines, based on the seed that I give it, the sequence of random numbers that's going to follow. So if I say seed 17,352, and then I call rand, if you do the same thing, you'll get the same numbers. If I want variety, if I don't want the random numbers to come up the same every time, then I need to seed it with a different number. And people often will just use seeds based on time. If I want reproducibility, where I do want to be able to recreate the same world that I created before, either because I'm restoring a saved game, or I don't want to save all that data out, or I want you to be able to play the same world that I played, then I can seed with a fixed number that I saved off and I remembered. However, there's a concern with random seeds in that they can be very fragile. And what I mean by that is, if you're not careful, for example, you could have randomness in all kinds of things, right? You could have the UI is sort of randomly flickering because it's got a candlelight effect. You've got particles that are flying off of it with random trajectories. Every single die roll breaks or disrupts the chain of numbers that you're getting out of that. So if you're doing your random map generation and someone's got the UI window open, or they pause it and they're pulling random numbers, now the map is going to generate differently because they're interrupting the flow of those numbers. So it's really important, if you are trying to get reproducibility and you're using random seeds, to be aware of that. And one of the most common conceptual ways of dealing with that is to have different random number generators. And you can say, seed this one for this, seed that one for that. Give me some numbers for world generation. Give me some numbers for UI, fanciness. And they don't pollute each other. Also, rand itself could stand a lot of improvement. It's not super fast. It's not super randomized. There have been considerable works and efforts done to make this better. The most popular one that's dramatically better and faster is the Mersenne twister. I recommend you check that out. Okay, so one of the things that when I was preparing this talk, I could not divorce myself from player psychology, which is, I find really interesting, even at a programming level, that psychology works into this. And we as humans have a lot of baggage when it comes to perceiving randomness and believing various things about randomness. So for example, we have classic fallacies: heads, 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 heads. What's the next coin? Well, obviously it's heads because we're on a hot streak, right? Or, obviously it's tails because it's overdue, right? When in fact, each event is totally independent. That one maybe is obvious to everyone in this room. Maybe less obvious is that this top one is more random than the bottom one. Obviously, false statement, but we can easily find ourselves in that trap. Players also have a real distorted perception of what percentage chances really mean and what randomness is. So for example, 65% chance, that's a safe bet. Sounds good. If everyone in this room went for a 65% chance, then all of you just lost, right? So 90% chance, well, that's almost guaranteed I should do that. I should lose very, very rarely, right? And 99% chance, if I have a 99% chance of hitting you, I should almost never miss. Certainly, I shouldn't miss twice in a row, right? And likewise, if I have a 90% chance of hitting you, if I miss you 4 times in a row, then there's something wrong. The game is cheating me. There's a bug, right? And really, if we just look at the math of this, if you've got a 1 in 10 chance 4 times in a row, to fail all 4 of them is a 1 in 10,000 chance, which is very unlikely, unless you have 1 million players, right? So that's one of the first interesting things, that even unlikely things are inevitable when you talk about the economies of scale that we have with our player bases. If your game has a 1 in 10,000 chance of something really bizarre going wrong, and you have 12 million customers, you're going to have 1,200 people-ish who are going to get screwed by it, and they're going to be posting about it angrily, right? So when you code something to be, well, that's really unlikely that that would happen, right? They're either going to get this, or they're going to get this, or they're going to get this. For them to go through that whole level and not get a single health potion, that's like going to happen. So there's a sense of luck that people have as well. And I think there's two aspects of it. There's what I'll call superstitious luck. My friend Mike believes that he is luckier than my friend Ben, and Ben agrees. There's also historical luck, which is I rolled below average tonight. So the second one is actually true in the sense that you can have an expectation for when I roll these dice, I'm going to get an average of 10.5, and I rolled a bunch and I didn't get that. So I did roll poorly tonight. There's another sense of player psychology that's involved in terms of loss aversion. The players really like winning big, and they like winning in general, but they hate losing big, right? So in general, this is why casinos are designed to lose a quarter at a time, and then suddenly you win $100. It plays on that loss aversion. So I want to go into expectation, and then bring this around to a couple different things. Expectation in probability is the chance of something happening times the outcome when it does happen. So let me posit a game here. You guys can play if you want. You pay me $1 to play. You can play as often as you want. You get to roll a 20-sided die. If you roll a 19 or 20, I will pay you $12. So is this a good game? So 19 or 20, that's 2 possibilities out of 20. I have a 1 in 10 chance. You have a 1 in 10 chance, I should say, of winning. So 10% of the time, you'll win $12, which means on average, you'll win $1.20. But on average, you're spending $1. So if you play this enough, you'll expect to win about 20% overall. That's your expectation for this game. So if I look at another game where I'm paying you $15, that's clearly a much better game. Right now, you're going to expect to earn 50 cents per play. So here's game number 3. You pay me $1,000, and you get to roll a 20-sided die. If you roll a 19 or 20, I'll pay you 15 grand. Anyone want to play? So the expectation here is outstanding, right? You're going to, on average, earn $1,500 minus $1,000. You're going to earn $500 per go. But there's a problem of utility, which is that probably not most of you have $1,000 in your pocket. And if you did, you probably don't have $3,000 or $4,000 or $5,000, right? So you'd play once, you'd lose, and then you'd be out $1 grand. So you don't have the kind of money probably on you, or maybe even in general, I certainly don't, to be able to play this game in order to get the expectation out of it that you might want. Another example, you pay me $100, you get to roll a 1,000,000-sided die. If you roll 1 million, I'll pay you $1 billion. So you should win on average $900 per play, right? But that's ludicrous. Really what you're going to do is just give me a whole bunch of money, or I'm going to go bankrupt. Now, that same game, if I were to give you $10 billion instead, well, obviously that's 10 times of a better game for you, right, than the previous one. The expectation is 10 times. But the utility is no different for 2 reasons. First, I'm not likely to be able to play the game to the amount that it is going to take to win the money. And even if I did, $1 billion is life-changing to me. And $10 billion is not 10 times more life-changing. Same problem if we were playing at a small scale. You pay me a cent, you roll a 20-sided die, I'll pay you 12 cents. Your expectation is $0.002. That's not even worth our time to sit and roll the dice, right? You can earn more delivering pizzas. So expectation shows its head in a lot of different ways. Let's say we're doing an RPG, and we've got 3 weapons, a dagger, a longsword, and Thor's hammer. And they do this much damage every so often with a delay. So if I look at the average damage per hit, Mjolnir does 388.5 damage on average. And if I calculate the DPS, which is the damage per second, clearly that has the best DPS. So which weapon is best? Well, it depends, right? If we're fighting 1,000 bats with at 1 hit point each, then a dagger is better. If we're fighting a boss dragon with 10,000, hit points, then the hammer's better. For fighting a pack of kobolds with 4 hit points, well, then maybe that's where the longsword shines. So utility and expectation are interesting to be able to think about. And when you're constructing how your randomness works in your game, and oftentimes your designers are going to lean on you to help them with the math of this stuff, these things really matter and the subtleties come out. Okay, another thing that's often run into with randomness in games is if we want something, but we don't know if we're going to be able to get it every time, so we want to just try to roll it randomly and, oh, that one didn't work, let's try again. So should we ever write code which says, try to do a random thing, and if it's illegal, try again until it isn't? So for example, let's say we want to find an evenly distributed set of points inside this circle. Well, if we compute the area of the circle compared to the area of the square, it's like 79%. So we have a 79% chance for any of those points in the square that they'll happen to be inside the circle. So if we say, well, it's pretty cheap to re-roll this, we're willing to, in the worst case, we'll re-roll it 100 times. And we can afford to do that. It won't slow down our frame rate. Then that will happen like every 1.6 times 10 to the negative 68, as in never. So that's a really safe bet. We're never going to have to roll this 100 times to get our choice. In fact, there aren't enough people in the world, in the universe, presumably, to ever demand that, no matter how many customers we have. But if we have a different case, like let's say we're trying to find points that are on the edge of the circle. And by on the edge, I mean, you know, pretty darn close. So say a 1 in 1,000 chance. Well, now if I do that same math, I may have to easily roll 100 times just to get a 10% chance of having it work at all. So that would be a terrible case. And what happens when I do that is if I have something that's unlikely and I try it and try it and try it again, then the computer will actually hang, right? And it may recover because it'll find a solution, but that will cause glitches in your frame rate. And I've seen people do this a lot. There's another issue with randomness, and I'm going to get into some more codey stuff here in a second, and that has to do with reloading. So you are the coder, you're the one implementing this, the user saves out their game, they turn off their computer, they reload their game, and then they go. What should you do with your random numbers? Should you re-roll them, or should you have pre-rolled them and have preserved them? If you re-roll them, then the player can save their game, open the chest, they don't like what they got, load their game, open the chest again, oh, they got something else, load their game, open the chest, oh, yes, finally, I got something great, save. So it allows them to manipulate the past, if you will. If you pre-roll, then they have a different problem. It allows future prediction. They save the game, they open the chest, there's a poison trap, they're like, wow, that was bad, reload, don't open that chest. And the only games that really don't suffer from this problem are ones that don't permit reloading, like permadeath, save and quit games. All right, so let's talk about different kinds of randomness, and we'll get into some code and math here. So there's one of the most common types is independent or isolation or replacement randomness. And this is like coins and dice, right? Each coin, each die has no effect on the other. There's no past, there's no memory. And there are a lot of ways in which this is totally appropriate to use. For example, at the AI Summit last year, people were describing the synchronized goats problem, where in Far Cry or something, they would throw a concussion grenade out, all the goats would fall over, count to 3, and then they would all stand back up. Right? So a simple little bit of randomness in there would help the goats look like they're getting up, not all at the same time. Ping pong kiting in MMOs, if you've got a character over there and a character over there, and they're fighting the monster and drawing the aggro towards him, and then this player draws the aggro towards him. If you make the threshold, the thermostat on which the monster decides to change his aggro, have some randomness to it, then it can break that pattern up and make the monster more interesting and more difficult. NPC skeletal variations, if you have models, you can stretch bones slightly, right? If you've got arms and shoulders and stuff in the hierarchy, you can have 1,000 orcs all slightly different. You can even adjust orientation so that some of the orcs are more hunched. And it really has a profound effect. There's non-replacement dependent randomness. This is when each random event does alter the probabilities of subsequent events. This is like a deck of cards. So if we're playing blackjack and I see there's a queen of clubs on the table, I know there isn't one in the deck, or at least I used to. Now they play with a whole bunch of decks at once. But you can still count cards. And when I'm playing no limit poker, I can see that I know that I have the ace of hearts, so that I know he can't have the ace of hearts. There are a lot of uses of this in games as well. For example, if you have a game with research and development, where your faction is like spending money and points trying to research new technologies, they could get really unlucky, and someone could have an awful game experience where they spent all this money on research and they never discovered anything, right? They're going to blame you, the designer, and the designer is going to come around to the programmer and say, well, how is that possible? That seems like that's broken. So if we use replacement randomness for that, we could basically say there's a deck of cards you get, and you're buying good cards to put into the deck, but they're going to come up eventually, sooner or later. And each bad result that I pull out of the deck increases my chances of getting a good result. I can use that for luck normalization, too. If I perceive that the player is getting bad luck, I can skew the results to give them better luck, which is an interesting and controversial idea. Also used for like non-repetitive playlists. I want a bunch of songs or a bunch of, say, audio clips, like I'm walking across the grass and I'm hearing crunch, 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 or different dialogue lines that the characters are going to evoke from a text file or from their audio file. I don't want to hear the same one twice in a row, but I don't want to feel like, okay, now I've gotten back around in the loop and now I know what the next one is. So by having that in a sort of deck of cards way, I can pull out the one that I just played, so I know I won't get it again. But I can play with the deck of cards in kind of fun ways to make sure that they'll come back around, but in a semi-organized way. Okay, so we're going to start with some basic functions. I am going to be referring to some of these as I go. Probably you all have this sort of thing. Get a random number from 0 to 1 is probably the most useful way to ask for random numbers in general. So one of the first curveballs on that simple random function is the idea of probability density. And that's the sense that not all the possibilities are equally likely. For example, if you look at the population heights, I'm probably in the top 2 percentile at 6'4", right? And there are far more people who are 5'9" than there are who are 6'4". So a great classic example of this is you have a 20-sided die, you roll it. Let's say we just ignore the 1, 2, 19, and 20. Or you roll 3 6-sided dice and add them up. So they both have a minimum of 3, a maximum of 18, an average of 10.5. But every gamer knows that the 3d6 has far more convergence in the middle, right? If we just try some tests in Excel, that's the kind of results we get. And specifically, mathematically, we get this curve. And there are a lot of different names for these curves, and we'll talk about some of them here in a second. But basically, what's interesting is that the density of the probability is greater in the middle than it is in the outside, right? And having non-linear probability density can be really useful for a lot of applications. If you go on Wikipedia and you look up this stuff, this is called the most common kind is called the normal distribution or a Gaussian distribution. And here's the math for it. First of all, it's not pleasing, but once you look at it, it's not fast either. It's e raised to a fractional power, right? And if I'm generating a world that has millions of blocks or millions of puzzle pieces or whatever, I don't want to be doing pow when I could be doing times. So I'm not a big fan, actually, of that. It's fantastically important for accurate statistical modeling. I don't think it's as useful in game programming. There are some other ones that have similar distributions. This Cauchy distribution you see here, if you look at the purple on the bottom, has a similar feel to the Gaussian distribution, but the math is much faster. There's basically just a divide. So for a 40th of the cost, you get 90% as good, if you're not exactly caring about perfection. So I think the best way to deal with this is to use easing functions or filter functions. And so if you have your random result from 0 to 1, that's the left case. That's linear. And then you just square it. Right? And now you have far more things closer to 0 than you do closer to 1. Or you can use smooth step, this smoothing function on the right, 3x squared minus 2x cubed, which is very fast. All right, so I'm going to have to speed up here since I don't have much time. I want to talk about procedural noise. So the idea of procedural noise is you put an integer in, you get a random float out. So for any integer, if I put in a 7, I will get back that same float. So it's really just like a lookup table, right? Except it's infinitely large and it takes no space. So the basic way this works, and I'll just let you look at the code later, is I take an integer, I mangle it up and smash around the bits, and then I divide it out and normalize it. I can do this in 2D as well, right? And I can just have an x position and a y position as my inputs, 2D input, and then still get back out a single float. I can do this for 3D noise as well. So when I do this raw, it looks something like this. There's just a random value at each point, but no matter how many times I ask for the numbers, they'll be the same. I can smooth that so that I can start sampling in between the bricks and get sort of nice transitions. Let's say I want to have a rolling hill. But the smoothing, just blurring it, doesn't do a very good job. I can use a rounded Gaussian filter for smoothing and get a better result. Or I can use a gradient vector Perlin smoothing, which we're going to talk about. And that leads to Perlin noise. Okay, so very quickly, Perlin noise, if anyone's not familiar with it, is really useful for all kinds of stuff. Here's some random landscape generated with it. Here's used for 2D game, where if the values are above a threshold, then it becomes a swamp, and if it's above another threshold, it becomes a mountain. Perlin noise is used for generating Minecraft. It can be used for clouds, all kinds of things. It can generate procedural textures that take up no texture memory. For example, this wood grain and the marble are generated with Perlin noise. And it can also be used to make things, again, like I said, feel more organic. So here, if we have grass that's kind of uniform in these rows and the tree is constructed maybe using an L system, which I'll talk about briefly, then it looks kind of computery. But if we just add a little noise to the scene, especially the grass, it looks dramatically better. It can also be used to make animations look a lot better. So if I just vary the actors' muscles and eyes and such with some random noise, they'll look like they're alive in a way that they won't otherwise. I can use them in shaders for visual effects. I can use them for cross-fading things. For example, here there's the road and then there's grass, and it's like this stair-stepped thing where it clearly goes from one to the other. I could use Perlin noise to make the edge between the road and the grass much more interesting and organic. So Ken Perlin is awesome. How does it work? Take noise, you smooth it, and octaves. What does that mean? All right, you take one of those noise functions, which I've provided for you in the slide. You imagine a large grid. You have noise at every point on the grid. And this is math, so we're not remembering these values. We just compute them and go. Then we use that as an angle, say 0 to 360 or 0 to 2 pi or 0 to tau, if you will, of the direction of a unit vector. So we get a bunch of unit vectors that are facing in random directions, once for each point in the grid. Those are called gradients. And here's some code to do that. We get the 4 nearest points and ignore everything else. In fact, we're only going to compute the 4 nearest points. And so there's this conceptual grid that we're inside of somewhere. For each nearest point, we get a vector from the point to us. We dot product it with the blue vector, and we get some number. And we do that at each of these 4 points. Once we've gotten the noise values at those 4 points, we interpolate them to cross-blend them to be within the block. So we figure out where we are in the block. We actually use smooth step, that filter function I said before, to bias it towards the edges. That gives it more of a rounded feel if you try it. And then we want to do just weighted averages to figure out the east value and the west value, and then combine those to get a total value. So effectively, the result is this, which is basic Perlin noise. And if we zoom in really close up, it looks kind of like that, because it's got a nice rounded gradient from point to point to point. Okay, so from a one-dimensional standpoint, this looks like controlled points with nice curves between them. So then the last component here of Perlin noise is octaves. So we do the same process again, except we do it now again with a grid that's twice as dense, and we compute that. And we have the values, so they're not quite as intense. And it looks like something like this in 1D and 2D. We do it again, and each time we're getting higher frequency but lower amplitude. And then we add them all up. So we get a nice, big, lazy, slow wave, add some noise to it, add some higher frequency noise, but it's less and less important. And the net result is what's called Perlin noise. And it looks great in 2D as well. All right, so that's how you generate it. Here's some code for it. So there are a ton of applications for Perlin noise. Obviously, people have used it a lot for terrain generation, for creating dungeons and caves, that sort of thing, for clouds. We mentioned wood, stone, marble, procedural textures, grass, trees, animation noise, and shader effects, right? But there's a lot of other things you can do with Perlin noise, like if you have stock market in your game, you can simulate it, or have trade values at the store that fluctuate over time. You can use it to create detail textures and normals, so that if you get really close to objects in your shader, in your scene, that they'll have really fine, interesting detail that's provided all from these noise functions. You can use it for generating coastlines, temperature and weather patterns. You can have the elves are really fickle this time of year, right? The kobolds are getting anxious. You can have actor heights and skins and colors, right? So that everyone in this audience is a little bit different in terms of our skin and our hair and our height and all that. And so that's why we feel plausible. You guys feel very plausible. You can use it for AI tunable parameters like my aggressiveness, my cowardness, right? So if some big thing happens, our leader is killed, or someone takes some big fireball, knocks out 5 of our guys, we might have a morale check in our game. And if we all turn and route at the same time, it's going to look stupid, right? So if you have tons of little variables like this, you can use things like Perlin noise to vary overcrowd behaviors, all kinds of stuff. So I really think it's one of the best hammers in your toolkit. So I'm running low on time, so I'm going to just plow through the rest of this really quick. Biased randomization is interesting. If you've ever played Dungeons and Dragons, your DM may or may not have lied to you for the good of the many, right? A blow that might have killed a critical character maybe missed when it shouldn't have. You can also use that to bias drops. So that instead of dropping a random item, I can drop 50% chance either a random item or one that I think will be helpful to you. I see you're low on mana, I'll give you a mana potion. Not always, but I can skew it a little bit towards you. It's really useful for dynamic difficulty systems, right? So if I want to do that, I can turn up the helpfulness or turn down the helpfulness of the algorithms by weighting those things. You can also use historically biased randomization, which I think is really interesting. It's a 2-hour talk on its own. But it's basically the idea that you can have different random number generators, which we've already said was a good idea. You can ask them, tell the programmer, the designer can tell them, I expect this result. And then every time that thing gets rolled, it keeps track of how it's doing. If it's underperforming, then it starts biasing itself more towards the expected mean. Just a ton of other examples of randomness in games. There's the southbound drunkard, or I guess in this case eastbound, where someone just has a chance of going east, north, south, or west, or east, right? And so just by doing that, it seems like they're wandering around in an organic way, but they're still going east like you want them to. If you're interested in plants, you should look into L systems, which are interesting. This diagram on the left shows you just start with a tree and start branching, and then you have randomness you can apply to how and when you branch. And it can produce some really nice, interesting results like these on the right. Cellular automata is interesting too, like Conway's game of life. There's no need for that to be deterministic. You can have a little fuzziness in there. In fact, someone implemented a fuzzy version of that on YouTube. It's a fantastic video. But you can also implement some randomness in there and let these things carve out space in a dungeon, right? We can use it for creating random levels. Fractals are a really interesting source of proceduralism and noise. You can also use Monte Carlo integration, which is the idea that I'm not sure what shape this is, so I'm going to throw a million points at it, and oh, it looks like a circle. So that's all I have time for, unfortunately. Thank you.